Dr. R. Sugurat Samuel is working as professor in physics in SRM University, Chennai. He is also training students for IIT JEE, AIEEE, and BITSAT. He has more than 16 years of academic experience both in teaching and research. He has published a book titled The Complete Handbook of Bachelor of Electronic Science Practicals. It is prescribed book in the syllabus for BSc Electronic Science by University of Madras. He has attended and presented papers in several national and international conferences and conducted many training programs and workshops. He has experience in both regular classroom teaching and also online teaching. His research areas are ultrasonics, polymers, crystal growth, and photovoltaic systems.
Welcome to UGC lecture series on Applied Sciences Electronics. We have been listening to a series of lectures on the subject Electricity and Basic Electronics for the BSc Electronic Sciences degree program. This is the first paper in the first semester of the degree course. This lecture is the 50th lecture in the series. We are dealing with the concepts related to electronics. In continuation to the previous lecture, in this lecture also, we are going to learn about one important network theorem. In the last lecture, we have learnt about the Thevenin theorem and the concepts related to Thevenin equivalence. We have taken up an example problem for understanding how a Thevenin theorem could be used or applied on a network to simplify the network. First, we learnt about the need for the network theorem. In continuation to that, in today's lecture also, we are going to learn about another important network theorem. Before we start today's lecture, let us see the session outline for this lecture. In this session, we are going to see the network analysis by way of the Norton theorem and how to find the Norton equivalent circuit, to find Norton current source and to find Norton resistance, which is represented as Rn. In the last lecture, I have given a brief on the necessity for the network theorems. We have even come across lots of network theorems available for simplifying the electrical or electronics circuits. One basic theorem also we learnt, that was the Thevenin theorem. And in today's lecture, we are going to learn about the Norton theorem, as I have mentioned in the session outline. Before we learn about the theorem, again I would like to emphasize on the need for the network theorems. We have already come across some of the laws, network laws, in the electric circuit lecture. After learning the Ohm's law, we have enhanced the way in which we analyze the electrical circuits by introducing two network laws, namely Kirchhoff's current law and Kirchhoff's voltage law. Those two laws alone are not sufficient for enhancing the network analysis, especially when it comes to the alternating current circuits. We require some more tools for network analysis. So, we have introduced the concept of network analysis. Without any proof to the theorems, we have just like that learnt the theorem and how to use the theorem for network analysis. For example, in the last lecture, we learnt about the Thevenin, how a two-port network could be replaced with a Thevenin equivalent components, namely the Thevenin voltage source and the Thevenin resistance, which are calculated on the basis of certain conditions and how those two could be connected in series to replace a section of the network. And in today's lecture, we are going to enhance our network analysis technique by learning yet another theorem called Norton theorem. Let's now see the necessity for network analysis and the theorems. Solving for currents and voltages in multi-loop electric circuits can be quite complicated, particularly for AC circuits. The voltage law and current law always apply, but using them may lead to long systems of equations. Certain theorems help with network analysis. That's what now we are learning. And let's see what is Norton's theorem and how to find the Norton equivalent components. What are the Norton components and then how to find those equivalent components. Let's first learn what is the Norton theorem for the two-port network. This is what is Norton's theorem. A linear two-terminal circuit can be replaced with an equivalent circuit of an ideal current source, which is represented as I suffix n, in parallel with a resistor, which is R suffix n. And here it is represented, and this shows a typical network. This network again might contain lots of electronic components, resistors, capacitors, whatnot. Even any number of components could be there in this network. But we don't bother about all that. The entire network could be replaced by these two components as it is stated in the theorem. One is an ideal current source. The current source is represented by this symbol with an arrow mark, a circle with an arrow mark, and here it is marked as IN. And another resistor which is connected in parallel to the current source, which is represented here as Rn. How do we represent a voltage source? We have come across such a symbol in the Thevenin equivalent. We have a circle in which a small sine wave, one single wave, is written or printed. That is the symbol used for the voltage source. But this one here we have is a circle with an arrow mark is representing the current source. Again, it's very easy to state. You remove the network and replace it with the two Norton components or Norton equivalents, namely the current source and the resistor. Current source and resistor should be connected in parallel. It sounds very simple when we say these two components could replace the entire network. But the real problem is how to find the current source and how to find the resistance, those two components which would replace the entire network. So here we need to learn the technique to find the equivalent IN and equivalent RN. So in continuation to the theorem seems very simple, but in continuation to that, we need to know how to find out the two components. How we have done in the case of Thevenin, the same way we will have to discuss at length how to find the current source and the resistor. Is there any condition under which these two are to be found? Let's further see. This again tells how do we replace a two-terminal network. So maybe this is a load and here we have a two-port network, and this two-port network is replaced with a Norton equivalent components, namely a current source and a resistor connected in parallel. And again the load remains the same. The previous clipping we have not shown the load, but here we have also shown the load. Now how to find the current equivalent current source? IN is equal to the short circuit current at the terminals, and RN is the equivalent or input resistance when the independent sources in the linear circuit are turned off and the load is open circuited. Again the terminologies like open circuited, short circuited are emphasized in finding the equivalents, because we have learnt the concept of open circuited condition and closed circuit condition in the Thevenin case elaborately, it will become very simple for us to understand the two terminologies we come across in the case of Norton theorem. How do we find the current value or the current source in ampere for the equivalent component of Norton theorem? Let's read the statements once again and quickly bring it to our mind what the short circuited condition and open circuited conditions mean here. IN is equivalent to the short circuit current at the terminals. When we have the two terminals, I would like to show the previous clipping and show the terminals here. See, these are the two terminals. Across these two terminals, we need to measure what is the current that is flowing. When we say the current should be provided a path. So, for that what do? We connect the two terminals with a short circuited condition. That means a connection is made, that is it. So, under that condition, how much of current is flowing? That is the meaning of this first statement, is equivalent to the short circuit current at the terminals. And I think the IR calculation is almost similar to the Thevenin equivalent resistance that is calculated. How the Thevenin equivalent is calculated? We need to keep the independent sources in the linear circuit in the turned off condition, or the load is open circuited. Once again, let us have a look at the terminals diagram and see what is the meaning of open circuited condition. See, this is how it is done. We need to keep these two terminals just open, that means no connection. We have to remove the load, totally it is to be removed, and under the open circuited condition, what is the resistance this linear circuit or the network offers for these two terminals, that is to be marked. I think we have even learnt an example circuit exclusively for understanding the meaning of turned off condition of the sources. That means, if there is a current source, that is to be short circuited, and if there is a voltage source, that is to be open circuited in the network. That we have done already in the last lecture. So, the same manner we need to find the value of Rn also. So, by calculating this In and Rn, we are now equipped to knock out the entire network and replace it with the Norton equivalent circuit. The two components are to be connected in parallel. That means, the current source and the resistor should be connected in parallel condition. So, let us see further how do we connect the components in the Norton equivalent circuit. So, this is how the Norton equivalent circuit is connected. Once the IN, here it is emphasized, it is a short circuit current. So, ISC, which means the short circuit current is the current here, and when the load is short circuited, we find the RL. When RL is 0, we remove the RL totally and find the RN, and this is how we form the Norton equivalent circuit. Now, after finding the Norton theorem, Norton equivalence, the input resistor, when the IN is equal to 0, that means RL is infinity, we remove the, it is once again explaining how to find out the Norton resistor. When the RL is infinity, we find a resistance, that is the Rn. See, this is how we open circuit everything and find the Norton equivalent resistance. How we have learned, how do we find the two equivalent components for Norton circuit and replace the network with the Norton equivalence. And these two could be done with a technique called source transformation. From the Thevenin concept also, we can learn how to find out the two Norton components. We will learn about that source transformation technique after a short break. Welcome back. We are discussing about the source transformation technique. What does that mean? In the case of Norton theorem, the current source is to be found, the value of the current source, which is comparatively little difficult to calculate the current when we compare the way in which we find the Thevenin equivalent source, the ETH. Using a voltmeter, we can very easily find the voltage across any two terminals rather than the current. For measuring current, we need to use an ammeter, but the current has to flow through a resistor. But in the case of the Norton theorem, we are finding the ideal current source. We are finding the current that is supplied by an ideal current source. What is the meaning of an ideal current source? Ideal current source is the one which does not have any internal resistance. But practically, when we have a current source, it will definitely have a internal resistance, and that will have an effect in the circuit when the source offers a resistance. So, we can find the Thevenin voltage value, how we find in the case of Thevenin theorem. The same way we have to find the Thevenin voltage value, that is ETH, which is represented as ETH, and after finding that, we can easily find the current value by dividing the Thevenin EMF value or Thevenin voltage value by the Thevenin resistance. The Thevenin resistance and the Norton resistance are one and the same. So, by dividing the voltage by the current, by the resistance, we can find the value of current. So, that is what is called the source transformation. By finding the Thevenin source, which is a voltage source, we can find out the Norton source, which is a current source. So, that is why the name is also given like that for this technique, the source transformation technique. Let us see what does that mean. In the Norton circuit, the current source is the short circuit current of the network. The current obtained by shortening the output of the network. The resistance is the resistance seen looking into the network with all sources deactivated. This is the same as that of the RTH, Thevenin equivalent. A Thevenin equivalent circuit can easily be transformed to a Norton equivalent circuit and vice versa. If the RTH value is equal to RN value, then the VTH could be written as Rn IN, and from that we can write what is IN. The IN is the ratio of VTH to RTH. Here RTH and Rn are one and the same, that is stated already. So, when we have this kind of transformation possible, then the Thevenin circuit is represented here like this and Norton circuit is represented here like this. There is a perfect correlation between the Norton current and the Thevenin voltage. And we should note one point here. I have shown the voltage source as VTH, whereas in the pure Thevenin circuit which we analyzed in the last lecture, I have used the notation ETH. Both the notations are invariably used. So, the meaning is the same. So, we are using both the representations here. So, this is the concept called source transformation. If we know how to find the VTH value, very easily we can calculate the IN, and that IN could also be used in the network analysis. We recall the following from source transformations. In view of the above, if we have the Thevenin equivalent circuit of a network, we can obtain the Norton equivalent by using the source transformation technique. Now, we have to see how the two equivalent circuits, that is the Thevenin equivalent and the Norton equivalent, would look like when we replace a network with these two networks. However, this is not how we normally go about finding the Norton equivalent circuit. It is just discussed for the sake of the theory. See, here we have the voltage source and the resistance connected in series for Thevenin equivalent, and in the case of Norton equivalent, we have the voltage source and the resistance connected in parallel. The order is immaterial because these two are connected in parallel. Now, it is time for us to take up an example problem for the Norton theorem and use the Norton theorem on the section of the example network and learn how do we find the Norton equivalent current and Norton equivalent resistance and how do we replace a particular section of the network. So, let us see an example problem. Find the Rn and In, the current flowing through the load voltage across the load resistor by using Norton theorem. First, we need to find out the Rn In and then find the current that is flowing the resistor here RL. What is asked? The current flowing through the load and the voltage across the load by using Norton theorem. We need to find out the voltage across the terminals AB and also the current that is flowing through this RL, which is a 1.5 ohm resistor. When we just superficially look at this network, very easily we can use the current theorem, current law and the voltage law, Kirchhoff's current and voltage laws, and we can find out the current in the load and also the voltage across the load. But this is an example problem for the Norton theorem. So, let us try to use the Norton technique and replace the remaining part of the network across AB with the Norton equivalents. So, the equivalent circuit will become very simple. There will be one current source and one resistor in parallel across the current source and again the load resistor, of course, which is an external part as far as this analysis is concerned. Now, let us see how do we approach this problem step by step. This is the step 1. Short the 1.5 ohm load resistor as shown in the figure. See, here we have short circuited the two terminals by removing the 1.5 ohm resistor. Now, this is step 2. Calculate or measure the short circuit current. This is the Norton current. We have shorted the terminals AB to determine the Norton current IN. The 6 ohm and 3 ohm resistors are then in parallel, and this parallel combination of 6 ohm and 3 ohm are then in series with a 2 ohm resistor as like this. See, when we look at this, the 2 and 6, no, these two are in the series connection and this is in parallel with the 3 ohm, and this is how we have to approach this problem. So, the total resistance of the circuit is the 2 ohm resistor in series with a parallel combination of 6 and 3. Let us have a look at the circuit once again. This 3 and 6 ohms are in parallel because these two terminals are shorted. The 3 and 6 are in parallel. That parallel combination is in series with the 2 ohm. So, the calculation goes in that way and we are able to find out what is the resistance. When we simplify, we get it is 4 ohm, and then the IT is calculated, which is also the current equivalent. So, it is V divided by the R Thevenin or R Norton, both are one and the same. We find that value as the 3 ampere value. So, I Norton is found, I equivalent is found out as 3 ampere. Now, we have to find the I short circuited I Norton by applying the current divider rule. So, that is what is done here. The IN we need to find out, which is flowing across the terminal AB. The previous current was the entire current supplied by the source, but now we need the current that is flowing through the short circuited section through this terminals AB. So, for that the same current 3 ampere is divided across this point. From this point, one current flows through the 3 ohm, another current flows through the 6 ohm. We need to find out what is the current flowing through the 3 ohm, which is only flowing across the two terminals AB, which is shorted. So, the current division concept that is used here, and we have found that value as 2 ampere. So, 2 ampere is the Norton current, which is represented here as IN. So, one variable or one component is found, that is the I Norton is found, which is a 2 ampere value here. Now, we need to find out what is the resistance in the open circuited condition. This is step 3. The open current sources, short voltage sources and open load resistor as shown in the figure for finding the Norton equivalent resistance. So, we have short circuited the voltage source and we wanted to find the equivalent value, which is seen through the terminal AB. AB should be open circuited. So, we find the equivalent value here. The 6 ohm and 2 ohm are in parallel, that is in series with 3 ohm. So, that is what is done here. To reduce that, we have reduced the 12 volt DC source to 0 by short circuiting, and which I have mentioned, the 3 ohm and 6 are in parallel, which is in series with the 2 ohm. So, that is calculated here as 4.5 ohm. So, now we have found the two components, the current and the resistor value, these two are used, and once again we have brought the resistance 1.5 through which we need to find the current and the voltage across that. This is the sixth step. The current is again divided here between the two resistors, the current flows. So, the load current through the load resistor is calculated using the current division formula, and we have found that value as 1.5 ampere. So, which is one part of the answer. The current through the resistor, load resistor is calculated. That current multiplied with the resistor, load resistor, will give us the voltage. So, that is also done in this step. Have a look at the way in which it is done. So, it is calculated here. So, quickly we have come across the way in which we simplify the circuit using Norton's theorem. I hope you have got an understanding about the Norton theorem. Now, it is time for us to see the summary. In this session, we have seen the need for network theorems, and also we have learned the Norton theorem with an example problem. Let us test our understanding by answering these questions. Explain the need for network theorems, state Norton's theorem, discuss how to find the current equivalent and resistance equivalent in the Norton equivalent circuit. Explain how well the source transformation technique would be useful to find the Norton equivalence from the Thevenin equivalence. So, with this, the network analysis is coming to a conclusion. From the next lecture, we will get into a new topic called the digital electronics. So, see you in the next lecture with the concepts of digital world. Thank you for